Hi, welcome back. In the previous lesson, we already imported the necessary asset for this course and did basic setup for this project. So in this lesson, we are going to continue to set up EQS system for AI to move. Before we get into the video, I want to briefly tell you about my new released courses on Udemy. If you want to create a 2D top-down vampire-like game in Unreal Engine 5, this course is for you. In this course, you will learn pooling system to handle large number of actors, random skills, shop system with save and load framework. We will create entire leveling up system with pickable items, 2 unique bosses and 20 more mobs during the gameplay. Moreover, if you want to learn action game on mobile device, check my action game tutorial course. Your own Sekiro-like basic combat mechanism from scratch by using Unreal Engine 5. Since players' mobile specifications are quite different, mobile game developers do need to optimize lots of assets and logics, including lighting, mesh polygons, textures, tick events, etc. You can play demo right now on Googleplay without ads. The link will be in the description below. Or you can head over to my Discord to check latest coupon for the courses. So in behavior tree, delete wait nodes. In the AI folder, create a new folder called EQS, abbreviation for Environment Query System. Let's create Environment Query class. Click Blueprint class. Let's create an EQS testing pawn first. This pawn is only for debugging purpose. It can visualize EQS results in the editor, which is very helpful for us. Rename it to EQS_tester. Open it. Let's add a billboard for this actor. It is only for debugging purpose, so we have to visualize it in the edit mode. I put it here. Next, create another new blueprint. Search env query context. Click this one, Environment Query Context Blueprint Base. This blueprint will be used to represent player existence. Well, it is an abstract class, only for calculation purpose. Open it. Click Override. Choose Provide Single Actor. We are going to call getActorOfClass node. Select Face Player Character, representing player character. Connect return value with return node. Leave a simple comment, representing player character. OK, back to Asset Browser. Duplicate this blueprint. Rename it to EQC_target_actor. This class is responsible for to get all the target actor instances from Blackboard. So from pin query actor, call getAIController. Next, call getBlackboard. I will add AI controller later. From Blackboard, call getValue as object. Specify its key name. Use make literal name. Copy this string, target actor. Paste it here. I add AI controller before Blackboard. From return value, since it is an object, it has to be casted to actor. If it is successful, this result can be passed to resulting actor pin. Compile and save. Great! We already prepared necessary files for EQS calculation. Right-click in Artificial Intelligence. Select Environment Query. Name it to EQS_AI_position. we are going to use this EQS file to decide where AI should move to. There is a root node in default, similar to behavior tree. Well, drag an arrow from this root node. We can see a bunch of preset nodes. We are going to use this node, points grid. It is a rectangular shape, which is useful in this case. Let's set its grid half size to 1000. Space between is 300. Next, we need to specify generate a round actor. Select EQC underscore player. These calculated or filtered results are surrounded with player character. However, it is not enough. We do need to specify the rules how to score or filter these points around player. We will do it later. Save all the changes. How to execute this EQS file in behavior tree. There is a preset node. Switch to behavior tree. Call run EQS query. This preset node is conveniently used in behavior tree. Select it. In the details panel, select a query template. Choose EQS AI position. There are 4 run modes. Generally, for movement, we prefer results from best 25%. So select single random item from best 25%. Next, how to visualize this result in the editor. Back to level, select EQS tester. Open it. In the EQS function, choose the template EQS AI position. Great. We see this light blue sphere appearing around the player character. When we unselect this EQS tester, these spheres are disappearing. We have to select this tester again. Next, we are going to create a variable in Blackboard to store results from EQS. In current case, EQS will return a location, so we need to create a vector in Blackboard. Open Blackboard, create a vector type variable, rename it to target position. Switch to behavior tree. Select this run EQS query task. In the details panel, we see the default value Blackboard key. Specify it to target position. In this way, the calculated results of EQS will be saved in Blackboard. Next, move AI character to this location. Call move_to node. Tweak acceptable radius to 30. Also check allow strife boolean. I forgot to change self-actor to target position. I will do it later. If AI doesn't see player character yet, call wait node. Also add wait node in the right of move_to node. Decrease its time to 0.3 seconds. Okay, how do we filter or score these points? Right-click this node. In the Add Test tab, there are several rules for us to choose. Any invalid results should be removed. Select Path Finding. This rule is used to discard unreachable points. It requires existing paths. Secondly, add trace rule. This rule is used to filter out results. In default, points behind obstacles will be reserved. Let's visualize it first. Change location of EQS tester under this obstacle. However, the green points, in other words, qualified results, are always behind obstacle comparing to EQS tester, which means in default, AI will always try to run in behind obstacle. If your game needs this behavior, it is perfect. How can we reverse this result? Actually, it is quite simple. Back to EQS file. Uncheck bool match. Save the change. Back to the level. The filtered results are reversed. Great, it is what we want. It is very important to keep this bool match to false in current case. Next, we don't want AI to move too close to the previous location where AI character is. Add distance test. Select it. Change its test purpose to filter only. Change its filter type to minimum. Set up its minimum value to 200. We don't prefer AI to stand at the same location for a long time. If new location is within 200 cm, this result will be ignored. Let's see the visualized result in the level. Around the EQS tester, there is a dark blue sphere, which means it is filtered out. During the game, AI character will not try to move there. It is what we want. If we increase this minimum distance, in the level, blue sphere numbers become increasing. In other words, AI will always keep moving. That is what we want. In the same way, we don't want AI is too near to player character. We want AI to keep some distance with player character. So we need to add another condition in EQS. Add distance condition again. Change distance to condition to EQC target actor and tweak this float value minimum to 300. After saving this file, these results will update instantly. Under player character, a blue sphere showing up, which means AI prefers not to move there. That's great. Let's try to tweak this value to 400. AI will not try to approach to near player character within its 400 centimeters. Switch to behavior tree. I forgot to change move to target from self actor to target position. Before we start to test, open BPAI. Tweak its maximum work speed from 600 to 450. Select character movement component. Search max work. Change this value to 450. For debugging purpose, we are going to increase sight radius of AI perception component in AI controller. Open AIC AI. Select AI perception component. Change sight radius to 10,000 and lose sight radius to 15,000. Half angle changes to 180. Even player character moves to AI from its back, AI can detect player character. Let's get started. AI is moving. Well, it seems that we need to fix its animations. We will do it later. Press apostrophe. Let's enable debug panel AI and EQS by pressing number 1 and 3. We are able to visualize AI preferred location. It looks good. AI keeps moving. When player character hides itself under obstacle, AI stops moving because it loses sight. If not, AI starts to select EQS results within best 25%. It keeps some distance from player character. That is what we want. Well, let's start to fix its animation blueprint. Open BPAI, select skeletal mesh component, find where its animation blueprint is. Duplicate this animation blueprint, rename it to ABP_AI. Back to BPAI. Specify this ABP/AI animation blueprint here. Open it. For AI character, we don't need these complicated nodes. Before doing so, I forget to change EQC player to EQC target actor. Switch to EQS AI position, select Simple Grid. Change this actor in Generate Around from EQC Player to EQC Target Actor. Then select this distance condition. Change EQC Player to EQC Target Actor 2. In the future lessons, we expect two groups combat with each other, so we replace AI target from specific player character to a generic target actor. OK, back to animation blueprint. Select these nodes, delete them. From try-get-pawn-owner node, call is valid node. If owner is valid, get velocity from this owner. Call vector ranges node, convert current speed vector to a float, pass its value to speed variable. Next, call calculate directions. It requires two inputs. The first one is velocity. The second one is the rotator. Get control rotation from owner. Hook it up. Promote direction value. Actually, it is an angle. Promote it to a variable called direction. OK, great. Switch to Asset Browser. We are going to create a blank space for this character. Right-click. In Animations tab, select Blank Space. Choose Face Skeleton. Rename it to ABS_face. Open it. Check Use Grid. Personally, I prefer to use grid in this case. It defines more clearly how these animations transition to each other. In the horizontal axis, type the name, direction. Its minimum value is -180. Maximum value is 180. In terms of vertical axis, its axis name is speed, ranging from 0 to 400. Specify wait speed to 4. The higher this value is, the quicker animation transition is. Uncheck smoothing since we are using grid rule for animation transition. Save the change. In the bottom right corner, Asset Browser, search idle. Drag it several times. Put it at speed 0. If you want to snap animation sequence to this grid, press key Shift. Search jog. Drag jog BWD to the direction -180 and 180. At speed 400. Drag animation jog FWD to the center at the speed of 400. Then drag jog left and jog right accordingly at direction 90 and direction -90 separately. Switch to ABP AI. In the event graph, make a simple comment. Call for these simple nodes. Compile and save. Switch to Animation Graph. Find output pose. This is the final pose of this animation. We don't need these preset nodes for AI. Just drag ABS face into this graph. Hook it up directly. Drag speed and direction variables into graph. Hook them up. Compile and save. Switch to BP AI. Make sure AI's animation blueprint is ABP AI. Compile and save. Let's try it again. Ooh, great! AI is running properly around the player with correct animation. That looks nice. Well, in fact, we also need to fix animation blueprint for player character. Let's do it in the next lesson. See you in the next lesson.